Thanks for hanging in there. So I'm Jimmy Williams. I'm a network engineer with Facebook's network engineering team, and I'll let Hans-Jürgen introduce himself.
I'm Hans-Jürgen. I try to take care of the hardware network engineering team.
So part of this, I think we'd like it to be a bit of a tour of, both how we went about building data center networks and like kind of the people that go into it. It's almost kind of think of it like a tour of going through your house, meeting your family, seeing the different rooms, seeing the kitchen table, etc. So first, how we build our network, that's one of the parts that I work on with a number of other people. But first, we have to start with what our buildings are and the fact that we have these large buildings, and these large buildings house our servers and our network. One of my favorite parts of these particular sets of buildings is this top plenum, where you have these huge fans for heat exchangers, and I think of this as HVAC at scale. And one of the really interesting parts is being part of the data center network team. When we started to build these up, we built management networks that went for these facilities, and we got to get a feel for what actually was going on inside of this HVAC system. And we get to tour these, which is also really cool. So if you want to get a feel for just how big one of the data center buildings is, this is our campus before we moved into it, or part of our campus now. And you can see that it's reasonably large, but this is what a building looks like on that campus. So it basically takes roughly half of what our campus was when we first moved into it. This is the one that's down in Menlo Park. So when we deploy these buildings, we actually deploy them in data center regions. We start off with a seed building, and we deploy multiple buildings here. And those regions collect those buildings, and we house the Facebook application in a collection of these buildings, which is our data center region. What this causes is the same graph that you've seen multiple times in multiple Facebook presentations. We have machine-to-machine growth that greatly exceeds that which is our machine-to-person traffic, the people that are accessing Facebook. So this is partially because every request that comes in basically has a large fan out that goes out for lots and lots of machines, and this causes this growth curve. And if you think about the fact that we have multiple buildings that are running at these regions, the amount of intercommunication between these buildings grows as the number of buildings grows. So this is very likely to not change, right? Barring any kind of interesting compute, settling out, but I don't see that happening either. So when you look at what that is from a network's perspective, and we'll kind of go back across a number of Facebook talks that happened, is up top we have our backbone, where Henry talked about express backbone, and then we have our building aggregation network that handles traffic between buildings and the interconnections into that backbone. Then we have our data center fabric. Alexei Andreev did a networking at scale presentation, I believe in 2015, to talk about the data center fabric topology. And then inside of that, we build our virtual clusters. And our virtual clusters are what house the legacy, well, I should say clusters are a legacy term that we use to assign inside of these fabrics, right? So because we used to build clusters in the form of network, now we just build out fabrics and we lay clusters onto them. So looking into what that is inside of a data center, it's really just a fabric of network devices. So we have a spine, we have server pods, and we have an edge. And those edges are what connect to our aggregation tier that I just described. And then we build those out into the form of planes. So how do we think about network engineering, and what is network engineering for us? Really, it's about taking that which is valuable, and this is kind of the purpose of any engineering function, is to take that which is valuable, use as little of it as you need to, and produce the most amount of product that you can. So in our case, we value people, we value power, we value space, right? And we value the available technology that's there. But this is in a particular order, and we put money at the bottom for a reason, right? because we want to keep up with growth, and we also want to provide reliability. Because notice, there is a reliable part to that network capacity. So this is what we're doing every day. Kind of a networking philosophy which ties back to like our company values is we want to build social value, and we're lucky enough to be able to do this type of event with everyone here today. We want to move fast, which effectively means that we want to be able to build and iterate quickly. We'll give lots of examples of this throughout the set of things because you'll find that we have a tendency to build something and find out it's not so good, and we'll throw it away, and then rebuild it. So we also want to be bold. This is kind of an interesting thing as you relate it to network. It's difficult for most network engineers to push software regularly when you work in a large vendor space because you don't get software regularly. Additionally, there's a certain amount of risk. So we try to work with that and push our own software regularly. We also want to be open with the people that use our network. So we'll talk about a couple of examples as we move through. But really what that means is making the network as approachable to the standard Facebook team, no matter who you come to, as we can. And then my favorite, we want to focus on impact. And impact for us is operations first, features second. You can think about it like people over protocols. So this should really say people helping people, because what we're going to go to is one of our design sessions that we worked into. And this is a roadshow. It's one of my favorite slides because you can see people from the software engineering team, the data center engineering team, the edge and network services team, production engineering, network engineering, testing. They're all sitting in a room talking about what we could do better on a platform and how we should introduce it. So it gives us an opportunity to get a full feedback loop with how we produce hardware and how we produce software. Why that matters is to go back to this. We have a lot of devices inside of a network fabric in general. So lots and lots of network switches. But the way that we design our network devices is every forwarding element has its own control plane. And that means that we have roughly a 12x factor for, like, say, a backpack device. We'll have 12 control planes, 12 forwarding engines. And those are where it sit in this spine, a server pod, et cetera. Another thing is when you have that many devices, you start to think about what is your truly minimum viable product, right, for the actual device itself. And you come back to things that have been talked about a number of times during these talks, like initial provisioning. So in the spirit of keeping things open, we try to make sure that we take the initial provisioning and work inside of the infrastructure that we currently have at Facebook. So luckily, we had a lot of server provisioning that was already in place. So we were able to reuse a good piece of that infrastructure. At the time, we had to build x86 hardware and a whole platform to get to that point because the white box market was in a completely different space than it is now. So we try to work inside of that. Additionally, we care about package deployment. Maybe 4 or 5 years ago, nobody was really putting packages or say RPMs on their switches. And this is really a common thing for us now, where we can put it on a number of different vendor switches, and the vendor market has improved quite a bit here. We also use this for process management. We had configuration management tools. And one of my favorites is statistics, how we get statistics from devices. This was another thing we were able to borrow from our application infrastructure and do streaming telemetry directly from the boxes. And finally, adding and removing not only a device from network service, meaning draining a device or taking traffic off of a device, but truly decommissioning a device. So early on when we first started doing this, we had the box and we had the hard drive built inside, and we worked on some different changes that maybe Hans-Jürgen can talk about. But if you look here on the right, and I'll stay on this slide for just a bit, what we have on the top here is our monitoring daemons. It's really Facebook's network stack. And what we have on the bottom is what is a typical network stack. And when you compare these, you get to get a visual for how we reused as much as we possibly could, what you see in the green, and then what we worked on to sort of add to that green, which is routing daemons, our FBOSS agent, and then the small red boxes, which I doubt anybody can see, ultimately say that we have a thrift RPC into each of these agents. And that's how we access these devices for process management, for statistics management, et cetera. So talk about how we handle configuration updates inside of this standard vendor environment. And I think it's worthwhile for everybody to kind of think through this, regardless of how you run your infrastructure. We took an early approach of doing full rebuilds for every device anytime we were going to make a configuration change. This is specifically inside of our data center network. And what this forced us to do is it forced us into a paradigm where we said, drain the entire device, do a full rebuild, then do an undrain. The reason that we did this is it's actually reasonably difficult to know if the change that you wanted to do was the change that happened and to be able to check that. So, and this is like a result of years and years of using the same CLI from like somewhere in the 1990s, probably before I started doing networking. So this works. It's a really effective way, but it's a bit slow. But when we own our schema, we own our configuration schema, we know that everything is going to be exactly as we expect. And additionally, we can do a configuration push and restart processes and then analyze the metrics that we go along with. So as we work inside of this space, it allows us to move a bit faster, make changes more quickly, and push agents more quickly. So another problem that we face inside of our data center infrastructure is power management. It's not to say that we don't know how to manage the power, it's just that power isn't an infinite resource. When you look at the data center power, we're always making these trades where you have these two backpacks here, and that roughly equals a small rack of servers. So every time we make that trade, we're taking away from the server infrastructure that we legitimately want to put in place. So ideally, we would work to reduce that power that we use for network to make more compute. Furthermore, when you look at where the power goes, this large, I think it looks like orange or yellow on your screen, is the ASIC or forwarding element that belongs to it, that belongs to the system, and that's the 59% of the power that we use for a given chassis. Followed by the interconnect, followed by the control planes. So the only way that we can facilitate really working forward on that power is to say, how do we reduce the number of control planes? How do we reduce the number of forwarding elements? And that's really a topology problem. Or on the other hand, it's a matter of working with different teams to figure out how to get chip vendors to reduce the power, reduce the interconnect power, and then we can work forward from that. Additionally, as we continue to work through this problem, it's a number of teams that we work with to pull this together between network engineering, hardware engineering, software engineering, our sourcing operations engineering team, and our forwarding engine suppliers, which is how we hope to reduce parts of this power. And now I'd like to hand it over to Hans-Jürgen.
Thank you, Jimmy. So what I'm going to do is we'll talk a little bit about how we build hardware. So this is not a classical talk about introducing you to a switch, right? Like there's been many really good talks and blogs on Wedge 100, Backpack, Wedge 40, and so on and so forth, and FBOSS. But rather it's about the how, right? A little bit about the what, but more so about the how. So first of all, and Jimmy mentioned that, is like an understanding about what really the minimum viable product is from end-to-end operations / layer 0 to 7 is actually key, right? Minimum means really minimum. That means on the physical layer, really let's not overbuild more than we really need. and then define clearly what a no goal is. I think that is really what we try to achieve from the beginning, and that is actually the hardest problem, a no goal, really focusing on what you need, and then making it really simple, scalable, and robust, right? Building something that encompasses everything is actually much easier, right? Actually, it's much easier to give a talk over 2 hours about a topic than over 10 minutes, right? So really focusing on what you want to achieve and really focus on that, right? So don't do things that is not really necessary. And that is really important from a physical layer, hardware layer, when you look at power, right? Power is actually becoming more and more a problem in the data centers, and then really defining what you need from a pure physical infrastructure point of view, the handling of the packets, reduce it, find ways of interconnecting in the most effective way. So how do we do that? So there's a cultural aspect to it, and when I look at that, is like clearly we need to pivot, think differently, innovate, but at the same time not always. So there's also an aspect of can't we just reuse what already works, right? So this is not a religion to just innovate and out-innovate. Have in mind this needs to be robust in the end of the day, and we need to make sure that this works in time at mass scale and with the right operational model. And for that, and you will hear that a couple of times from me, and I show you a couple of examples, a continuous feedback loop around really understanding where we are and we should be, literally from anywhere in the company and the community, is extremely important. So having said that, and Jimmy showed this beautiful picture of people working, and I just can really relate, because sometimes it's just late hours, right, to just sit with everybody in the room. And it comes, innovation and this whole operational model really comes from everywhere, but especially from DC Ops, of course. The guys who actually day-to-day work and try to keep the fleet running. And so getting that connection as an engineer, right, is the most important thing ever, right? That is my experience. And really making sure that anybody who is actually developing stays on it. So don't hand it off. Just and run away, but rather it's actually a pretty learning experience if you're a hardware engineer or software engineer and you stay on it and you're on calls, because you actually have to live with your code, right? You have to live with the hardware you're building. It's a very healing experience for the next design or for the improvement of the current design. So really, nobody is from my perspective who works in engineering can be detached from the actual impact of what we're doing. And then, of course, at some point in time, though, after scaling, there is also a new phase coming. And I think that's the moment where you start celebrating and really making sure that everybody understands the success. So this culture sounds trivial at times, but really it is about the behavior or the processes we try to drive, right? We don't, well, at least I try to avoid the word process, because it kind of feels like you pretty much put somebody into prison. But actually there's some level of understanding that everybody who goes into engineering builds, right? And at the same time somehow comes up with a framework of impact. And so that's one of the reasons why we look at building very fast to what we call engineering validation test units. So a first phase, I'll show a couple of slides in a moment what that means exactly. And really not about just linear thinking, right? Because linear thinking means you define something and then you build something and you continue to build it towards MP, but it's rather a permanent loop that we try to do, and that with very small and very, very fast moving teams. And that's kind of like what I would call the development process. I said it's process. Essentially, it starts from the left, right? Discovery is really understanding if it's worth pursuing. Very small teams trying to figure it out. And you can see this loop back. Sometimes you just have to stop and start again, right? And then we try to, in the next hack phase, we try to lay the foundation to really move forward, to get to what we call a plan of record, to actually move forward to full mass production that goes through the classical industry terms of EVT, DVT, BVT, with engineering feasibilities, design implementation, and product implementation to mass production. And that is kind of I think, the classical product, but I think the beginning is the ideation or innovation or whatever process you want to call, and the end is rather the classical discipline engineering product to really get, in a fairly disciplined manner, things to production. But it can, especially in the beginning, be stopped. And that's actually a big thing here, because there's no predetermined development path, right? We need to make sure that we can stop and reset at any time where it just makes sense as we go forward. And that can happen at any point in time in this process. And so that's why it's sometimes confusing when we actually explore things, but oh my God, we hit a wall, we built something, wow, that doesn't work. Next time it works, and by the way, we give it to the software guys and they start iterating and we improve on the hardware side, it kind of becomes like an us that this project and process is then, when it hits EVT and so on and so forth, gets really into mass production. So having said that, especially the beginning, the discovery process and the hack are kind of key in the starting of what we want to do next. And it's really, sometimes you just don't understand where the problems might lie next year, right? So discovering and coming up with hypothesis is really important. I will give a couple of examples how we did that in publicized projects. And then as we move forward, really involving then more people into a hack phase that then leads into the next steps. In all of this, feedback is like key. Loops, feedback, understanding, question yourself. So we really like to teach us in that direction as everybody comes with a hypothesis and believes it's right, and then we start asking questions in operations, asking questions around, and do a real 360 and then end up, wow, it is actually right, or wow, it's actually wrong, and we have to stop it. So what are we really talking about when we build our network? Jimmy showed a couple of slides about the network itself, of the planes, and how complex it is, how large it is. But really, what we're doing is what people say is disaggregation and integration, right? We take a monolithic block and really try to divide it into smaller entities that are modular, flexible, right? That we can, and are best in class, allows us to really get a better life cycle model. And those blocks can be anything, right? It can be also varying over time, right? A block in there could be a switch, it could be a chip, it could be a software module. But in the end of the day, we need to have a wrap around it to actually make this thing work, and that is the integration part. And one of those examples for disaggregation is the separation of software and hardware. Really, this is all what we're doing in the end of the day, is like disaggregation and finding the right way of integrating. And so that's where we start off. One of those blocks, right, could be a Wedge 100, a switch. And I like to give some of those examples. A Wedge 100 is, as we envision it, is a top of rack. It's a 32 times 100 gig. It has certain features. I don't need to go through all of those elements here, but in essence, it's what I would call the minimum viable product, right? For description you can get, but it's a lot more, right? Even though we were focusing on the fundamentals, after all, it's a 3.2 terabit switch that can be, as we figured out, used in many other tiers, and not just within Facebook, but all over other, globally, all over other places. And the fundamental behind it, I'm nearly embarrassed to show this slide, is essentially a CPU. It's an ASIC switch, clearly, the board design, the BMC. It's what we call switch element and the optics. So essentially, you end up with this switch element that is a very versatile. It's nearly a Swiss Army knife for everything we do in networking. So it comes down to the basics. And when you look at that in detail, how we actually build this, it's essentially consists of many other items that are what I also consider as a level of disaggregation, because we can actually very quickly change heat sinks to have a better thermal, maybe for the optics, or we can change the CPU, or we can change even the switch. So we can actually fairly quickly, from a hardware perspective, probably from a just EVT quality perspective, in 3 to 4 months, change any of those elements. And that gives us a huge freedom. I consider this also some level of disaggregation, because it allows us the freedom to basically pick and choose what is best in class and what we need in production in time. Another example for how we try to actually use the data center environment and the operational environment we have is the optics. So it's actually interesting when you just look at optics and production of when you actually produce those optical pluggables. What really helps those manufacturers is narrowing the temperature range. Optics doesn't like, lasers don't like temperature ranges, very high temperatures, and they don't like humidity. So these are the two aspects that we can actually fairly nicely control in data centers. So we decided, at least on the temperature range, that we actually narrow it, and we gave the specification has been submitted to OCP, and we've built an ecosystem around us so that this also reduced a little bit the reach. This exactly fits our environment. And our problem statement, our minimum viable product. We don't need more. That's what we wanted to get. So the next is, and I'm wearing this shirt, you can see that on the back, right, is the backpack. It's essentially consisting, and Jimmy mentioned it before, consisting of like 12 wedges, logically, right, and 12 control planes. So essentially it's a closed structure, 128 times 100 gig switch. Fairly similar product description as the Wedge 100, is just a little bit larger. And we did basically the same thing, minimum viable product, and we worked through the chassis. And you can see the mechanical design is a lot more complicated, right? And I just want to give you a couple of examples that this doesn't come overnight, even though we had within 3 months from start point to EVT, the first working products in our house, right? Not GA, not high quality in the sense of, but something ready for software to innovate on. We had a lot of iterations around mechanics, and just wanted to show this mechanical design. So you can see on the left side, there's this more off-the-shelf components that we used in terms of handle. And you can see on the right side, we had to actually custom design it to make it a lot easier to handle. And that came out of our roadshows with data centers. So we essentially went to data centers and said, hey, how does it actually work for you? And we figured out, hang on a minute, we actually have to put a number. You see the little 1 on the right side? So that people actually press that button first before they push the handle, so that this comes out first, right? So there is, we actually did this intuitive design with them together, and improved over the manufacturing. And that's actually big, because many of the problems we see in handling is just taking line cuts out and don't destroy the fiber that is plugged around it, right? So this is actually a big problem. It doesn't sound so much when you are in the classical software engineering practice, but actually down on the ground in the DC ops teams, these are real problems. And so we try to solve that with them. Here's multiple more examples. So on the left side, you see also an SCM CMM card, and the design totally changed. And here, mostly because the left side, it turned out that the force you need to apply to get this card, to rip out this card, is so high that you actually destroy other things. And we just worked through this in this process with the DC Ops guys, and came up with a total different handle. Or here, a fan tray, same thing, same situation. We went through multiple iterations, beginning and end, looks very different. Or last but not least, chassis mid-frame design on the left side. And then to the right side, where we have a lot better air throughput, and it's much easier to manufacture with our suppliers. So it's not necessarily DC Ops operations thing, but also with suppliers, right? So we collaborate with suppliers in this time frame. So I'm not saying this is unique to us versus an OEM. I'm just saying there's a very intensive iteration process going on at any point in time in this process. And here's another example that I like to show is for very fast iteration in the hack design. Last year, we essentially, within 6 months, we started from nowhere to actually field trial outside Facebook, right? So to build what we believe is the first switch router and transport white box in the world, and we just actually submitted that also to TIP. It's essentially a DWM product, metro and long haul, with up to 4 times 200 gig on the line side and up to 12 times 100 gig on the client side. And you can see the remarkable similarity to Wedge 100, and that is actually for a reason. I mentioned before, we want to move fast, we want to be bold, we want to hack quickly, and we want to get things done. So at the same time, we don't want to reinvent everything. And this is a good example, I believe, where we actually reuse quite a bit. So in this case, we actually reused quite a bit from Wedge 100. And so here you can see in green is essentially what we made as a change. And the rest we just basically reused in terms of some of the software, some of the and most of the hardware we reused, and just because we didn't need to reinvent it, and it turned out to be a very nice and dense product. So in summary, we try to live the values that the company has given out. I believe it is absolutely amazing that we can build social value. We do share the work we are building. And we try to collaborate with the wider ecosystem. That allows us also to do those conferences like Network at Scale, and really to try to develop with the open standard, open bodies like OCP and TIP, something that is bigger than a single company. But also move fast. Move fast means, everybody knows what it means. We want to move fast. At the same time, we need to move fast and land somewhere. And that is only possible with a continuous iteration and self-questioning of what you're doing. And just a couple of examples were those mechanical design changes, but there's so many others. I think this is the opportunity to really pivot, but at the same time really land somewhere is only possible if you develop the culture of feedback and diversity. I think everything I said only works jointly with a comprehensive operation model. And an operation is first, features is second, means really also that software is key to operation, and it's pushed all the time. But the hardware and the software model need to match perfectly in the sense of you saw this disaggregation model. Yes, it needs to run somewhat independent and disaggregated, but at the same time it needs to somewhere match. Be open means also we need to make this network very approachable to people in the ecosystem. And our collaboration and reach out to TIP, OCP, and other bodies is really helping all of us, I believe, to drive the next level of networking. And the example in our case was basically that we try to drive this backpack and Wedge 100. Many software companies are now putting software on those hardwares. So, and last but not least, I try to reiterate it, is like the operation model is extremely important to us. And sometimes it is very difficult to understand if you sit in your corner in the office as an engineer, what it really means. So operations is first, because at that scale and with this robustness, the understanding, all of it is key. And sometimes it's funny because like fiber, right? We have thousands of miles of fiber in a single data hall, not just building, right? Just understanding, what problems this really, means from a day-to-day handling can actually destroy the entire operation concept. So there's a lot of things like that we are trying to tackle and also reflect back to the community. Thank you.
Hi. In your network design, how much redundancy do you consider? Like considering applications should also move fast, fail fast, and also recover fast. Like when you design the network topology as well as your hardware, do you consider redundancy as a requirement? or do you push that layer to the application folks?
Both. When you look at the fabric or the data center fabric that was on the board before, there's a number of redundant nodes in that piece of infrastructure, but there's also single point nodes where we have rack switches that are like full rack. So we sort of work both sides of that problem, both on the application side. I mean, I can pass it to Hans-Jürgen to talk about the hardware redundancy that's built into the system, but at a network level, like we run routing protocols and we can change routing protocols as we like, but ultimately, when there's a node failure or taking a node out of service, we should never see traffic impact as a result, right? Like, and that's something we constantly strive for. But there's redundancy in control planes, there's redundancy in forwarding planes, there's redundancy in power supplies. It's all over the place. And it's not just a matter of redundancy, but it's also a matter of running things hot and running traffic across multiple links and getting the amount of capacity that you need. So if we were to decide that we wanted to turn up, instead of 4 planes, go to 5 planes, 6 planes, 7 planes, 8 planes, that's completely possible given that we have that trade-off of power and network. Right. Do you want to hear the hardware section? Like,
Sure.
Sure.
So backpack, that's on my back, right? Is actually 3+1 redundancy, right? It's like 4 line cards, 4 fabric cards. So essentially, if one card fails, right, all the other cards are essentially redundant. Plus, where this is positioned in the network, it's essentially even when a full backpack fails, you would have enough redundancy. So it's like 4 posts to sign, but that's also reflected inside the backpack. And depending on your equipment choices, you even can have multiple controllers. And you can see that essentially, as backpack is also consisting of 12 Wedge 100s, right, with CPUs, each CPU on it, and so on and so forth. It's essentially an autonomous system of 12. So it's actually intrinsically fairly redundant. So you can actually find a lot of redundant paths. So in summary, it's we built redundancy on several levels. Clearly, and you mentioned it, Jimmy, the top of rack, right, is essentially a single granular point of failure, of course. But so that is being avoided on a network and application level, that you actually see actual experience failures. So having said that, that also means still, even though you have redundancy built in, we have to make sure, and that's why we have a fairly disciplined process, starting with EVT from my perspective, to actually land quality hardware and monitor that quality in production, right? So I just want to emphasize that has nothing to do with redundancy, but rather with quality work that needs to work. Not for 20 years, but probably for 3 to 5 years.
Thank you for sharing and your experience and presentation. Question I have regarding is, with the wedge, you can build a backpack similar topology with a 12 wedge. Apart from power, cooling, and cabling, is there anything else which was considered to build a backpack? Because you could essentially do the same thing with 12 wedge individual boxes. And the second question is, where would you place it in your environment? As a definitely not the top of rack, edge fabric, where would you place backpack instead of 12 wedge?
So I'm going to decompose the first question a little bit. Like, if you were to take 12 wedges, you would ultimately take a certain number of RU to facilitate those 12 wedges. And additionally, there's a certain amount of cabling complexity that comes along with that sort of infrastructure. So in part, it both takes up more space, maybe not more power, maybe a little more power based on the cables that you use, but not like significant. But we do care about the real estate that we have for the switches themselves. And then additionally, there's another aspect that we didn't put a picture in here for, but along with the hardware team, the network engineering team, like works and says, like, when we do one of those road shows that we showed the picture for, we walk through how we would bring those switches into our environment. And our first pass at Backpack, like, we've got a lot of really great feedback that was effectively like, this just isn't going to work. in the way that we were doing it. And so that feedback was around how many components we brought in individually. And a number of people on Hans Jürgen's team worked on making that particular packaging much better. So, I mean, it's a bit of a trade-off, right, and how you work with it. So I wouldn't say that decomposing those into 12 like true independent wedges is necessarily like a bad idea. It's just like you have to look at that trade-off that you're making for both like how the system arrives, how it comes out, and then like what you're going to build as a result. I think that was your first question. What was your second question again? Oh, yeah. I mean, basically, like, you know, the upside of like 12 wedges is you could grow, right? Like, because you could say, hey, you know what, 14 wedges is maybe the right distribution. But where we actually place it in that topology is anywhere upstream of the rack switches itself, and they act as an aggregator for us. So in our standard network terminology, it would be sort of a fabric switch, a spine switch, an edge switch, and those are all places where we could do that, right? As you get higher and higher in the network, maybe 12 wedges isn't enough. Yeah. Yeah.
Hi. Thank you so much, Jimmy and Hans, to share this insight. I really enjoy listening to it. And really love to see that number one, number two, design, the backstage stories. And my question is redundancy, just like the first question. And this is also related to the Henry's original talk about 4 planes discussion. I really enjoyed that.
Yeah.
And my question is it from day one? You had this redundancy from day one, or if not, what was the changing point or a lesson you guys can share to move from doesn't have any redundancy to the current redundancy model?
So at the network engineering level, we always had some amount of redundancy, but there's always a battle of whether or not you manage the capacity to stay the network capacity to stay in front of the redundancy that we have. And I think early on, like a long time ago, we had sort of a 2-post layer 2 like base network, and the amount of redundancy that we saw in that system was much less than a 1+1 scenario, mostly because there's a certain amount of overhead, how you felt like things over, and that's why we moved to this like sort of larger 4-post model or 4-plane model to speak to Henry's talk right around express backbone. So as a network engineer, you're always managing redundancy, but you're always battling network demand. So you can always miss something there. So it's a constant battle, I should say. So there wasn't a turning point. It was just a constant battle from the first day, and it continues to be a constant battle.
And in that sense, let's say a downtime experience gonna push from moving toward to the redundancy side of the discussion, or it's more like constant debate?
Well, it's not a constant debate. Right, we run a service, and to kind of go back to the original point, is there was a certain set of inputs, and the output is reliable network capacity. So when we look at reliable network capacity, reliable is a key word there, right? So if we set up a number of things that we've talked about externally, like Net NORAD, for instance, where we constantly measure the loss and latency through the network, and if we see that go to the side, we effectively manage that through a SEV review, and we try to figure out how we can improve it. So this is part of like doing the operational management. We just always have to be improving, right? And there's never a turning point. It's just keep your head in it.
Thank you.
Yeah.
Thank you so much.
You're welcome.
Hello. Fantastic storytelling, guys. Seems like you're really not only doing design, you're thinking like designers as well. From a kind of point of view where you actually care about the ones that you design for. So congratulations to being people-centric instead of technology-centric. My question is not about technology, it's about the culture, because you talked a lot about the culture here. How did you come about this culture, which is clearly a way of creating value rather than achieving goals? Yeah, how did you iterate that as well, or did you take a concept that was super cool or whatever?
Oh, this is such a super difficult question to answer. I will try. I don't think culture stands still, right? Culture never stands still. I don't know if you come up with the same principles in 5 years. It's driven by the people, right? And actually, I believe it's the combination of culture and goals, right? Without this culture, you wouldn't achieve the goals, right? So it's very difficult. Sorry, I can't really answer this question, but I can also say that also with my background where I came from before, right, more classical OEM vendors, right, it's very difficult to make the transition. It takes a while, right? Yeah. And also feedback needs really to come. We need to create a feedback culture, right? Like that's really open, and I think that is really the transition. And it's every engineering team, especially hardware. And we try to. You can see software has a culture, right? And we try to take those cultures now into the hardware domain. You can see when we fast iterate, that's not hardware usually, right? So we will also not iterate overnight, but rather probably over weeks, right? So that's kind of like, we're still, of course, slower because we actually deliver hardware, and that building hardware, right, something, a box that you can actually touch in a layer 01 is a lot harder, right, like in terms of timing, but we try to establish similar cultures and behaviors. I think it's rather an adoption of the software model, right, into hardware, than expanding on the hardware models that you see classically out there.
And you had a problem with the word process. I would like to give you an alternative, and that's a structured approach. It still has structure, but it's still just an approach, which means that you could decide to approach it from a different point
I take
of view.
that.
As long as you can rebuild the structure. Yeah, I mean, I think that's the key to like a lot of these slides, right? Like, there is this process, but I think as long as we're willing to admit that like we're not right for infinity, and that we're able to change that constantly and make it better, then I think we're still on the right track.
I had a question for you. You mentioned redundancy at all layers in your network. How do you deal with redundancy at the top of rack switch? Do you have dual NICs on the servers?
No. So maybe I missaid that, right? Like, but we run a single top of rack, and at that particular place, we can take that rack out of service, right? Like, so we can drain the services that are in that rack. But additionally, when we're doing software pushes, we don't necessarily want to drain everything that's in a rack because some things are stateful. So we try to stick to a warm sort of like upgrade approach where we're able to upgrade the software hot. And it's a strategy that's more built for speed as opposed to like built for 100% completeness.
So when you upgrade the software, I assume you keep the forwarding intact. If you have to change that, can you share any information how fast you can do that? How fast you can have the software upgrade by rebooting the tour? Is it like sub-minute, 30 seconds, 20? How long does it take?
Well, I'll say that it's less than a minute, right? Like in some cases, right? But it's not always less than a minute. But the specifics, I kind of want to withhold it for somebody else to present that's been working on that piece of infrastructure for some time, and I think they can do a really good job presenting it at a future at-scale event.
Thanks for the presentation. So we've been building resilience into routing protocols for years and years. We all remember non-stop routing, graceful restart, non-stop forwarding. We can be talking about it for months. So about 3-4 years ago, we started to move resiliency more into application layer, making them stateless, bringing more survivability into application layer. In your case, are you doing the same thing with your applications? Do you see requirements coming from service team to networking team changing in terms of reliability, in terms of capacity, in terms of number of nines?
So it usually doesn't come across like that, right? Like, and I think sometimes this is also like a cultural miss, right? Like that we sometimes can miss on the network engineering side. We can assume that the application should do it, or the network should do it, should take care of redundancy. And the reality is, we both care about keeping up capacity so people can use Facebook. So we should continue to work on both fronts. Now, when it comes to resiliency in the routing protocol, whether or not that's Grace, like, and all the other variants of like nonstop forwarding, right? Like, we shouldn't sacrifice simplicity or operational simplicity, and this is something we usually take, is if something becomes a lot more operationally complex, we'll try and stay away from it, right? Because it keeps us from like constantly sinking cost into something. But I think to answer this question, I would say it's not an either or, it's an and, right? Like for us, right? So we work as a team inside of our infrastructure to try to keep the services up. It usually doesn't come across as like this should be exactly 5 nines, right? Like, because we still keep this team atmosphere. Does that answer your question or no?
To some degree, so.
Okay.
But is there movement from less complexity into networking into more complexity within software layer? Do you feel it in terms of interaction with software team?
Well, we work with the software teams too. So like, what's interesting here is that we are both writing software and we are both doing networking. Some of us are writing much more complex software than others. Like Peter writes more complex software than I would write, as an example. You know.
All right, we'll take one last question.
I have 2 questions. The first, will the backpack and voyage be submitted to OCP? And
backpack is submitted to OCP as well as Wedge. Yes, so you can download all the files, you know, all the designs, everything from the server.
Okay.
It's open.
Thank you. And you're talking about cost a lot of time. I'm wondering how much percentage of the components you used are commercially off the shelf, and how much, just please, if you can give a ballpark estimation, how much hardware cost of the boxes?
Yeah, it's very difficult to quickly come up with this, but most of it is off the shelf, right? So for instance, the electronics, the switch chips, you just can buy it off the shelf. I mean, all of this can be basically bought off the shelf. You can see also that as we submitted the optics, right? You know, you talk about cost as is the biggest cost driver known in the industry. We submitted a specification, and several vendors comply to that. So this is also essentially becoming off the shelf, right? So the idea really is to make it off the shelf. Clearly, from a hardware design, we had to make changes, right? You know, as you can see from just pure handle, these are really the exceptions where it's not off the shelf, but you have all the drawings, anybody can build it.
Okay, thanks.
Thanks, guys.
Thank you.
All right, well, that kind of wraps it up for the day. I hope everyone really enjoyed what we had to present today. We're going to be sending out surveys. We really, really want you to fill those out. Tell us what we did well, what you'd like to see, what we did poorly. Especially, don't complain about the Wi-Fi, because it'll be the same next year. Actually, I would like less of you to complain about it next year and get your vendors to fix it, especially if you work for a networking company that provides those VPN solutions. You know, as another note, we'd love to see a more diverse set of speakers. We're continually trying to find more people to come and talk. So if you have anything interesting to talk about, you know, we'd love to, you know, review it, allow you to present. You know, we're only as good as we share. You know, all of this stuff is not proprietary. It's not anything that gives us competitive advantages. It only makes our costs go down in our industry that much better, and that's the reason why we do these events. So we really want to encourage more people to come and share, more people to do, to talk about what they're doing, and personally, more people doing IPv6. Thank you very much.